Get started. So, welcome everyone. My name is Vasa Dasan. I lead the appointment team here, and welcome all the sales team from radio detection. We have today a presentation about GNSS theory and practice by Peter Schreier. Peter is our chief scientist, and he's also a professional engineer. So he knows the theory and also what is used in practice. So take it away, Peter.
Awesome. Thank you, Vasa. I appreciate the introduction. And I just welcome everybody to the webinar. I'm going to go through some high-level, understanding of GPS and GNSS systems. I'm going to use the term GPS and GNSS kind of interchangeably. Technically, GNSS is all the satellite navigation systems. There's a GPS, Galileo, GLONASS, and the various regional ones, but they all have kind of the same ideas and concepts the same. So if I use them one or the other, consider it to mean both of them. It makes no difference. So essentially, GPS. GPS is a series of satellites about 12,000 miles above your head that are orbiting in what's called a medium Earth orbit. There's 32 of them right now. We use 24 of them as active satellites, and there's the 8 that are held in reserve in case one or another one goes down or has some issues or has an orbital issue. This does happen. Satellites do go in and out of, what's called healthy status all the time. It's not something you as a user have to worry about, but what might happen is you might see a satellite just suddenly drop out. Not unusual. Your receiver will understand what's going on and switch to another one or ignore that one. And I'll show you how that's accomplished from your receiver end of things. Just as a background, I'm going to probably go for about 30 minutes here and leave some time for questions at the end. But if you see something that you're have a burning desire to ask at that point in time, feel free. I'm here as a more of an interactive webinar. So again, feel free to ask questions, bring something up that's of interest to you, anything of that nature. For the most part, this is a webinar about GPS systems. I'm going to reference, of course, some ways that ProStar PointMan software is using this, just as an example, so you can see what real-world data looks like and comes from, and you can kind of appreciate more what it takes to get a position from a satellite. Again, these satellites are 12,000 miles above your head, so it's the fact that you're actually getting an accurate position from this is just a miracle of the modern age. This is something that started back in the 1960s, came to fruition in the 1980s, and at this point in time is very ubiquitous for most companies in the geospatial sector. So there you go. Again, what is a GPS? Like I said, it's a GPS satellite, a bunch of satellites, 24 at this point in time, orbiting the Earth. What you see in the picture there is a very broad concept of what we're looking to get. GPS is nothing more than a way of getting a position based on trilateration. Trilateration is the ability to say, okay, if I'm X miles from this point, X miles from point B, X miles from point C, then I can basically use basic geometry and algebra to figure out where I am. In this case here, we need positions from at least 4 satellites, and I'll go over why we need 4 in just a minute here. But just look at what the picture here shows. The green dashed line shows, okay, the GPS satellite knows how far it is from the center of the Earth, center of mass, to be honest. When you put a receiver up or start a receiver up, you're basically getting a position or how far away you are from the GPS satellite, and that is the orange dashed line. That is what you're receiving here. What we really want is how far you are from on the surface of the Earth from the center of mass of the Earth, the yellow solid line here. That is actually what your coordinates are. I'm not going to go into the coordinate systems until the very end, but in essence, all we want to know is this yellow line. How far are you from the center of Earth? That is your coordinate system. So if you look at it closely, it really is just a basic geometry problem. If you know the distance from the GPS satellite to the center of the Earth, you know the distance from you, the receiver, to the satellite, you can figure out the third leg of it here. Now, how you figure out the distance from you to the satellite is a simple formula on the outside. If you know the time it took for the signal to get from the satellite to you, you know how fast that signal was moving, speed of light, then you can figure out the distance. The problem is the time is not quite constant and the velocity isn't either. In addition, there's certain errors that you have to account for. And I'm kind of going to go through each of those in a little more detail. But just know that in essence, this is a geometry problem wrapped up in a whole bunch of relativistic effects and quantum mechanics and everything else we don't have to worry about. So the satellites. How does GPS work? From a basic overview here. First thing we have is a bunch of tracking stations on the Earth. These are run by the US Department of Defense and its allies. And what they do is they monitor the satellites very closely. What they do is they use their tracking stations and radar to determine the orbits of the GPS satellites. One of the things we have to have in high precision and know this is where are the GPS satellites located? And how are they moving? Are they stable? If they're not stable or there's something wrong with them, they are basically set to unhealthy and another one will take their place. But the critical component is we must know where the GPS satellites are. That is handled by the stations on the ground run by the US DoD. So the US DoD basically transmits new orbital data, time corrections, and locations of all the other satellites to each GPS satellite. The reason it transmits the locations of other satellites is to allow you to rapidly locate and receive signals from other satellites once you've got the first one. I have a kind of a scale on the right-hand side there showing you what each individual signal is from all the satellites. There's something called a carrier wave. That's the top one there. That is nothing more than exactly what it is, the carrier, the frequency that carries the entire message. In essence, that is not really the navigation message or the information on it. It is just a carrier. We use it to get position in a different manner, but for now, just consider it the carrier. The second one there, the red line, is the actual signal that you get that shows the positioning information. It's called what's called a PRN code or a gold code. This is unique to each satellite. So each satellite has something unique to this that is different from every other satellite. This is required because GPS satellites transmit all the satellites on the same frequency. There's two or three different carriers, about 1.5 gigahertz. So we have to be able to distinguish between satellites, and how we distinguish satellites on the same frequency is they have a, if you want to essence and call it, a different signature between each of them. As well, they also have this little green line here, which contains things like the navigation, the orbital information, the timing information. That is something that the command center transmits up to each satellite, and you will download so you can find out where the rest of them are, in addition to some other information. So that's number 3 there. The GPS satellites transmits the time information and orbital information down to Earth. And that is what you're receiving at your GPS receiver. So the piece that you're seeing is a very small piece of the overall effort it takes to put these things in orbit and continue with them. So in this case here, you need at least 4 satellites to be able to get a position. Why do I say 4? Because there's 3 spatial unknowns, X, Y, and Z. But in addition to that, You also need a time factor in there. So you need four. You have four unknowns. You need four satellites to actually get this information. Time is actually the most critical piece of all of this, because the GPS satellites have on board what is called an atomic clock. It's accurate to about a billionth of a second. The reason for that is that speed of light being 3 times 10 to the 8 meters per second, if you're off by a billionth of a second, you're off by 30 meters. Okay, and that's obviously not happening on GPS. We're actually much better than that. So that is why time is the most critical component of this. And interestingly enough, time synchronization is the most common usage of GPS, not positioning. If you look at any ATM or financial transaction around the world, they are all time synchronized and time stamped using GPS clocks. So they use that methodology. On your wristwatch or in your cell phone or anything else like that that has GPS capability, that is how time is calculated on your system, on your watch, and your cell phone. What you essentially have in your cell phone is one of the world's most accurate clocks once you have a GPS signal, because like I said, the GPS signal from a satellite is an atomic clock, extremely accurate. The GPS signal, time circuit in your cell phone is a 25-cent piece of silicon that is accurate from second to second, but over a day loses way too much. So consider that. The reason we need at least, say, 3 once we have time is that if you're looking at position, the satellite tells you you are 10,058 miles from satellite A. So you're on this red line somewhere, anywhere along here. You get a signal from the second satellite, this yellow one, satellite 2. It tells you you're 10,062 miles from satellite 2. So the only place you can be is where these two intersect, here or here. Not sure which one. All right, so you need a third one. It goes, okay, you're 10,082 miles from satellite 3. Well, the only place you can obviously be is at this intersection of all these 3 circles. Now, unfortunately, it's not that simple. You do not know exactly how far away you are from those satellites. There's lots of errors that come into effect. And you may not know exactly where the satellite position is, so you have some issues there. So both these problems have to be solved. I have a bit of a graphic here showing you, and this is a scale, where the GPS satellites are. There's the 3 here, GPS, Galileo, Compass, and GLONASS are in what's called a medium Earth orbit, about 10, 11,000 miles up. And what that means is they are outside of the magnetic field of the Earth here. And I will go over the reasons for that a little bit later on when we discuss some of the errors that we have. Look at things like the Hubble Space Telescope, the space station, Iridium satellites. They're well within the magnetic field and very close to Earth. The reason GPS satellites are so far up is it allows you to have a much more stable orbit, and that is much more critical for them than being close to Earth and being inside the magnetic field. If you look at communication satellites, they're generally up at about 25,000 miles, 36,000 kilometers up. Again, the reason for that is they stay stationary over a portion of the Earth. GPS satellites have what's almost a 12-hour return cycle. So that means every 12 hours, you'll start repeating the cycle. You'll have the same satellites over your head. And if you want to get a full and complete data set of all GPS satellites, you leave your receiver running for about 11 hours and 56 minutes, and they'll come back on you. I don't recommend that. That's an overkill of all information. Generally, we leave it for only a few seconds. But for setting control systems and everything else like that, we use what's called a PPP process, precise point positioning, and that allows us to get high precision information. Okay. Ground control systems for the GPS, these are critical. If they weren't for these ground control stations monitoring and uploading data, GPS would fail within hours or would not be usable within hours. Orbits are stable but vary within their orbit. So we have to be able to monitor and upload new data. Prime control station is Schreiber Air Force Base in Colorado. Vandenberg is its backup. Hawaii, Cape Canaveral, Diego Garcia, Guam are the secondary control stations that monitor and can upload. And technically, the only one that is allowed to upload data is the Schreiber Air Force Base. And it's just for security purposes. I know there's lots of movies out there that tell you, we're able to control and, move and do all sorts of interesting things with GPS satellites. Yeah, that's Hollywood. It is really not practical or possible to do that. So if you hear that, it's not going to work. What is a GPS signal? Again, GPS is a microwave range signal, 1.5 gigahertz for an L1 band, 1.2 for the L2. Each GPS satellite transmits, L1, 3 different bands, L1, L2, and L5. The reason we need, more than one is because they do transmit at different frequencies. All GPS satellites transmit L1 at 1.5 gigahertz. All GPS satellites transmit L2 at 1.2 gigahertz. That's what I mean by that. We need to have 2 different frequencies to understand how it transmits through the ionosphere. Go through that in a minute here. Essentially, this center graphic here shows all the errors, the major errors that we expect from a GPS system and why we have them. This red centerpiece here is kind of what we're seeing from the GPS. We're saying, okay, you are, I'm sorry, this is in metric. This is just how we do things here, 20,000 kilometers away from you. But in addition to that, there are certain errors inherent to that we have to account for to make it the true range from you to the satellite. GPS satellite moves at about 4,000 meters a second, so extremely fast moving satellites. We have to account for that. That's kind of a Doppler effect. And also the fact that by the time the GPS satellite sends a signal out to you, and by the time you receive it, that satellite has now moved about 300 meters away. That's 330 yards. But there's, I'm not going to go through each of these different errors. The only ones that we are really concerned about, and then we have some effect on, and we have to watch for on the ground, are the ionospheric and tropospheric delays. These are due to the atmosphere. The troposphere is from here to about 6 to 8 miles. Ionosphere is 6 to 8 miles up to about 70 miles up. And there's 2 different types of delays and issues we have with that. How do we get an actual, time from the GPS? How do we say, okay, the difference between the time that's arrived and time it's sent? The GPS satellite sends out this, the red signal that I made up here, the PRN code. In your receiver, you are also, monitoring that same code, one for each satellite, up 24 of them. When you receive it, it's slightly offset from the time it's sent. And that's actually what you're doing. That's the time of propagation. It was sent at T1, you received it at T2. I'm simplifying a lot of things here. So this is the time it took to get from satellite to you. Multiply that by the speed of light. That's what's your geometric range here. From that point, we have to add all these errors and figure out how far away you are. You get that same thing from another 3 satellites, you now have a position. And that's it. In a nutshell, is exactly what GPS is doing. Now, what we have to look at and understand here is on the left-hand side. You're assuming that the GPS signal to you, from the satellite to you, is this dashed line, straight distance right to you, no reflection, no bouncing off anything, just right to you. Fortunately, that's not correct. You may be getting some signals that bounce off a building, bounce off, almost anything around will bounce the signal, and then you'll get it. This is incorrect because this is now taken slightly longer to get to you and will obviously cause you problems. You can get a total obstruction of satellites away from you, so you don't even see that. to be honest, that's not a huge issue in getting a position if you have enough other satellites. I will go over what's called a DOP value as an error message later on. You can see where that affects it. Also, the GPS signal is what's called refracted. It doesn't go through the atmosphere straight. And that's primarily to do with the ionospheric delay. And I'll go through that. But I just wanted to show you, there's a lot of different error messages and error propagation that we have to look at. But the GPS system and your receiver will take care of most of them once it has a reasonable lock-on system and how it's working. A quick overview of the two main errors that we have some control over or some understanding of as a receiver on the ground. Again, troposphere from here to about 6 miles up can give you an error about 2 to 20 meters. That is actually the easiest one to model, surprisingly enough, because the lower part of our atmosphere is mainly water vapor as the error problem. And we can model that using various mathematical formulas that do a really good job on that. And to be honest, you may say, oh, the atmosphere, lower atmosphere varies quite a bit. Not really as far as a GPS signal is concerned. It's actually very consistent and homogeneous, so we don't have to worry too much about it, but it is there. The ionosphere is the critical one for us. Last couple of days, we had a solar storm coming from the sun. These are harmful to the GPS satellites themselves, not the issue we're discussing here, but what they do is they cause the signal to either slow down or bounce around in the upper atmosphere. That actually is a significant problem for GPS. We're coming to what's called solar max. It's a normal cycle from the sun where you get a lot more flares coming down. You'll see that what happens here is in this lower left corner here, you're getting signals from L1 and L2, two different frequencies on that satellite. And the reason we need those two different frequencies is that the delay is, I guess, mathematically modeled by two different frequencies. If we only have one, we can't model it because the amount of the delay is dependent on the frequency. So this allows us to model, and I always use the term model because we cannot exactly understand it. It's way too variable up there, but at least we can model it and understand it and mitigate it as much as we can. When we have a solar storm, we're not mitigating this as well as we can. In actual fact, you could get, 3-4 yard errors easily enough in what's called a G3 storm. And then we've had a few of those this year. If your clients are coming up to you and saying, hey, I can't get either a lock on the satellites or my position is off and this and that. In a lot of cases, that could be the problem. Only one way to mitigate that. Stop collecting for a couple hours, try it again. There's nothing we can do about that at this point in time. So, all right, kind of go over what we mean by accuracy and precision. I've been talking about that a little bit in the last little while. I'll try to define that. Positional accuracy, horizontal and vertical, same concepts, but they are treated separately. Okay. Accuracy is how close you are to the true value. Okay. Precision can be thought of as the repeatability. That's your grouping. If you take a bunch of measurements, how close are they together? Ideally, you want high accuracy and high precision. If you have something like, the one on the bottom left there, low accuracy, low precision, which means you've got a large grouping and you're nowhere near. If you took enough measurements, you would know, even then, would be nowhere near the center or the true value here. So ideally, we collect measures of both of these within PointMan, and these values are actually coming off of the GPS receiver itself. Internally, it calculates these values for you on any receiver. And you'll see that up in the little display I have on the left-hand side here. In this case here, I have an accuracy of 0.1 meter. Okay, that's not great, to be honest. We can get better, but this is just an example. And I'll show you why it's not that great just because of what's we're using here is the RTK. Now I have a horizontal precision value here of 0.62. That is not a meters, feet, US feet value of any form. This is a ratio. What you want this to be ideally is less than 2. Okay, 3 is still okay, but ideally less than 2. We separate precision, and accuracy in horizontal and vertical. Okay? And we collect both of those here. The reason we separate these horizontal and vertical separately is because GPS treats them separately. Okay. Horizontal accuracy is usually better than vertical. The reason for that is that if you're in a horizontal, you can have satellites all around you in the entire sky, and they encompass every angle you can think of. Vertically, we don't have satellites on the other side of the Earth, so you have nothing holding you there. So vertical accuracy is always going to be worse than horizontal. Usually it's about double. In this case, it's not, but you can expect double. Not unusual. I have an item here called confidence level. And I always want to bring this up because what a lot of people fail to understand, and what manufacturers of GPS receivers always say, oh, we're accurate to 1 centimeter. And that's kind of great, but it doesn't give you the full story because there's different ways of expressing what's called the accuracy, the confidence that you have. How, for lack of a better term, how confident are those measures that accurate? There's something called a 95% confidence level, and that's what you should be striving for. What that means is 95 times out of 100 measurements, your position will be within that value, within 10 centimeters in this case here. A lot of times they use what's called a 1 sigma value. That means 67%, which means 67 out of 100 times you're within that accuracy level. So just understand there are different ways of stating things, and you have to be kind of confident that you're getting the right one. I'm going to quickly go over what are called GNSS correction services. These are ways that we mitigate the errors. In essence, how we get rid of the tropospheric, ionospheric errors in some of the clock functions and everything else like that. 3 different ways of doing it. There's one called autonomous. That's the top one there, the GNSS system. That's if you just turn on your cell phone with no other GPS system on it, you can expect 10 meters accuracy. There's something called an SBAS, S-B-A-S. That is kind of a North America-wide correction service, but it's very, very basic. Most times your cell phone will use it, so you can get down to 1 to 3 meters accuracy. Only the cheapest cell phones will not use this. But to be honest, it's not really what we in the surveying industry would use because it's not accurate enough for our uses. There's something called, the first level of true correction services is called DGNSS, differential GPS or GNSS. It's the one I've got there on the top left. What you have is a base station, which is another receiver set up over a known point, and it's receiving signals from the satellites. They're not, because it's set up over a known point, it's getting a position from the satellites that says it's slightly different. Okay, no problem. It looks at those, it says, okay, how do I correct for that? Transmits that to your roving GPS receiver and says, okay, using these corrections, you are now this instead. This is kind of the first level of correction services, and it works down to kind of the foot level, no better than that. The farther away you are from your base station, the worse it's going to get. Once you get above, about 30 miles, say, well, then those corrections aren't exactly applicable anymore because the signal is now going through a different part of the atmosphere and has different effects on it. That's why you see both the DGNSS and the RTK will get worse as you go away from your base station. You come to the second part there, what's called RTK, real-time kinematic, or network RTK, same concept applies. In this case here, not only are you solving the, for the correction services from the signal. You have a rover and a base, just like the other one, but you are looking at what I'll call the carrier phase measurements. Basically, you are tracking the carrier wave. You are tracking the number of wavelengths between you and the GPS satellite. I'm not going to go into a lot of details on that. Suffice to say, this is the realm of expensive receivers. This is not, your Garmin or receiver that's worth $200 or $300. These are now the $1,000 level receivers that can do this. It allows you to have a very high accuracy. One concept I want you to remember from this is there's the idea of a fixed and float solution on GPS measurements from this. And our PointMan software will tell you whether you got fixed or float. Fixed means you now understand how many wavelengths you have from you to the satellite. Float means you've got some noise and you aren't able to do that. Also means you're too far away from your base station in some cases. So, just take away that concept. Fixed and float means float means you're too far away from your base station and you need to get closer and you can't get quite as accurate. Fixed means the best level. You can get high accuracy, and this is really what you're trying to do. So for most cases, network RTK means that you are paying for a subscription for this, and your corrections or carrier phase measurements are being sent to you via radio, or the internet. Both work that same way. But it differs from differential GPS in that it uses a different structure of the signal. And what you're trying to do is have an RTK system on a short baseline. You'll notice there, you can get centimeter level position, half inch to an inch, depending on your receiver. Same thing applies though. The farther away you are from your base station or your network station, the worse it's going to get. The final one here is something that many GPS manufacturers have set up. Trimble has their Catalyst system. Hexagon has a system, Hemisphere has a system. And what they've done is they've set up base stations and reference stations all over the region that they're looking at. It could be worldwide. And they monitor signals from the GPS systems themselves and do modeling based on that through their own network control systems. They uplink that information to communication satellites, and you are basically bringing that down, the GPS signal and the corrections from a communication satellite. This allows you to have a much larger area of coverage. It can be regional, depending on the GPS manufacturer, or there are some worldwide ones. You are not going to get quite as accurate as RTK just because of you're modeling over a larger area versus a very regional area, depending on what you're going to do it. But these are subscription services, and you're going to pay for them by hour, by month, by day, and you're going to be paying for them depending on the accuracy you want to get. Just a quick overview of that. This is from Trimble, but it shows you the different types of systems they have. Autonomous, again, that's not a system per se, it's just whatever it is. The SBAS, that's what I mentioned up there as well. 2 meters, consider meter a yard, thereabouts. And if you go into the baseline RTKs, you can get far better. Again, you're looking at 2 centimeters, just under an inch in horizontal to about 1.5 inches in vertical. Again, we bring those out as different accuracy levels. The Trimble RTX, that is kind of a point-to-point PPP system, global system. Depending on what you want to pay for, you can get anywhere from 1 inch to 1.5 foot, depending on what you're looking for, and about 2.5 inches, depending on your vertical. One last thing I want to go through is this what's called initialization time. In most cases, it's an instantaneous, which means as soon as you get a signal, you are getting that level of accuracy on the signal. If you go into a subscription service, this may not be the same case. It may need to collect enough data to perform a model adjustment. That could be anywhere from under a minute or under a minute to about 20 minutes, depending on what you're paying for. So when they tell you, oh, we can get 2 centimeter or 1 inch accuracy, well, there's another thing you need to ask. Are you sure? And how long is it going to take to get me? Once you have initialized, the next point you go to is instantaneous. But the problem is if you lose lock on satellites, go behind some trees or buildings or something like that, and you lose lock, you have to reinitialize, and that could take a few minutes. So just be careful on what you're looking for there. You notice on our PointMan software, we will tell you what type of fix you are getting. In this case is an RTK system, and that is reflected in your accuracy. So about 4 inches there is what we're getting. So we will, if you had an RTX subscription or something of that nature, it would show up here and you get a fixed or float solution. So this goes down to, under an inch quite easily in most cases. So just understand that, this is fully and fundamentally dependent on your GPS receiver and your correction service. This is not a function of the software. This is just exactly what we're getting from the receiver. One last thing I want to go through is coordinates. I haven't really gone through that because it's not a fundamental idea behind GPS. GPS is basically saying this is how far you are from the center of the Earth. Generally, you are getting what's called latitude, longitude. I'm sure you've heard of this before. This is, basically the angular, measurements from the center of the Earth, latitude, longitude. That is a theoretical value, okay? What generally we want to do, we store in PointMan that raw data, because from that raw data, we can make calculations to do any other coordinate system. You're generally going to want to have this in some kind of state plane or UTM system. PointMan will allow you to specify what's called EPSG, European Petroleum Standards Group. It's a way of indicating which projection you want, whether it's a state plane system or whatever else. This case here is called a NAD 83 2011, and this is the epoch. Don't concern yourself on this. Generally your client is going to say, oh, I want to use this one or that one. So we support several hundred of them. They're all available in there. But just remember, at the base, we always store the raw data, so you can change this at any time and see your coordinates in any type of system you want. Okay. Last thing I want to go through is vertical. Vertical is treated differently. Vertical measurements, are derived from your latitude, longitude, absolutely as well. But if you want to, if you tell person you're at 50 degrees latitude and 40 degrees west longitude, they don't understand how high they are from whatever surface, whatever they're expecting. So that have to be derived differently. In PointMan, we have several measures of height, if you want to call it. There are two critical ones we have to look at. These are ellipsoidal height and geoid height. GPS by default will give you height above your ellipsoid. Ellipsoid is just a mathematically defined surface derived from satellite orbits. It just kind of generally encompasses the shape of the Earth. It is the reason GPS uses this because GPS doesn't know there's an Earth there. All it is concerned about is the singular point at the center. So we have to basically give it, okay, the Earth is represented by an ellipsoid, and we go with that. Most people want, height above mean sea level. That technically is what we call the height above a geoid. And we have to basically calculate that. And what we do within PointMan is we ask you to tell you which geoid model are you using. In the US, the standard one is called Geoid 18B. There are other ones as well, and we have all of these within PointMan. All you have to do is select them. If for any other reason you see a bunch there, I would always recommend just use Geoid 18 in the US. This geoid is not something we calculate. That is done by the US federal government, and it basically says, okay, what's the difference between the geoid and ellipsoid? Applies that, and off you go. If you see things like, ellipsoid altitude, which we have there, and so your altitude being the same value, that indicates you're not using a geoid model. That's fine, you don't have to, but just understand your height is not going to be compatible with maybe what your client is looking for. In any case, we store the geoid height, or sorry, the ellipsoid height, because from there you can calculate everything else that you want. And that's all there's to it. So in essence, really, this is the basics and fundamentals of GPS or GNSS systems. There's a lot more information I can go for, and if you have questions on any of this, I encourage you, please contact us. Give you our support number here. They will, either answer your question or send it along to me, and I'll be happy to, do whatever I can to answer your questions. Again, my background, I've been 25 years in the field as well as doing development work. So if I can't figure it out, I probably have the contacts that can. So with that, if there's any questions, feel free to speak up and I'll do what I can for you. Nothing? Hello?
If anyone has any questions, please do speak up. Or raise your hand on the chat channel. Or you can type in the question as well.
Nothing. There is no way I was that clear. Excellent.
There's some questions here, Peter.
Okay. I don't see any. Maybe I'm missing. Oh, Q&A.
The chat window.
Okay, RTK and RTX. Okay. In essence, RTK is a generic term, real-time kinematic. RTX, in this case here, is Trimble's implementation of RTK. Basically, they're using the same measurements, the same ideas, just transmitting and on their what's called their RTX network. They're both the same thing. One's just a proprietary name for it. Which fixed type you reference accuracy use? Yes, you do. If you have a fixed solution, your precision and accuracy will both be lower than if you have a float solution. The reason that if you generally have a float solution, if you have a lot of noise in your signal, that noise will affect your grouping because it's going to jump around quite a bit.
Hey Peter, they want you to read the question because they can't quite see the questions.
Oh, okay, I will do so. Sorry. The question was, with fixed type that I've referenced, accuracy, do we see a similar effect with precision? Yes, it will be very linear. If you get a float solution and your accuracy is, goes from say 5 inches to 2.5 inches, your precision will do, very similar. Your precision will be cut in, grouping will be half as big. So it's very linear. No questions. Just want to say thank you. Thank you. Welcome very much. How our future RD8200S will be able to communicate with your solutions. The 8200, and how any GPS or any locator communicates with the point man is via Bluetooth. So the Bluetooth, basically, you are sending from the RD8200 both the locator information and the GPS signal information that you're getting. So we will basically be taking both those streams of data and putting them together. From a GPS standpoint, there are standard messages that come from every GPS receiver. That's been all standardized across the industry, and that is how we get all that information. The information that you saw in the screens here, I'll bring this up. Go back like on the right-hand side here. All this information is standard information from a GPS receiver, whether it's the RD8200 one or a Trimble or a Leica or everything else. So that is how it's communicating with us. Okay. I can't see quite. Okay, sorry. I will read them out. And the first question we went through was the difference between RTK and RTX. Again, RTX is Trimble's implementation of RTK. Can we get OSTN 15? Yes, we can. And I believe it's on PointMan now. You can just select it. How do we load GeoIs into PointMan? You can't do that yourself, generally, because they are national systems. If you have a specific one you want, let us know. We'll load it for you. It really only takes us a matter of, a few minutes given to us.
And we already have a bunch of geoids already loaded in Australia, in Finland, and obviously US and Canada.
The OSTN 15, I believe it's loaded already. If not, I'll check on that, but I'm pretty sure if not, we'll have it loaded. It's a standard one. We have the Canadian ones loaded there as well. These rarely change. So, and when they do change, we will upload the newest versions of those allowed to use them. Is Geoid 18B a standard no matter what software you're using? Yes, it is. This is a standard Geoid for the US market. There is also a Geoid 09 and an 03. They're just earlier iterations of those. We do have those within PointMan if you're in an area where the client is asking for that. So these are standard, we don't define them, we don't develop them, we don't support them. These are from the US federal government. So if there's an error with them, well, it's consistent. No problem. All right, what we got here? Ken, I heard different terms for what survey grade GPS. Can you narrow that down for what is accepted as survey grade? Yeah, unfortunately, that survey grade is a very gray area. As a surveyor, I am a licensed surveyor. What I consider survey grade is under an inch vertical, under an inch horizontal, under 1.5 inches vertical at 95% confidence. Okay. That is not something I define. That's something that's generally defined in the field of what you're looking for. What that means is that you're not going to be able to use a cheaper receiver. Survey grade means you're 2 or 3 or higher number of frequencies from multiple constellations, and that it processes and understands. If it's noisy, it'll reject measurements and things like that. Something a cheaper receiver may not be able to do. So, survey grade also means the person handling it has to understand what they're doing. It's not just the hardware, it's a surveyor who understands, okay, why is my signal being blocked? Well, because you're standing beside the wall of a building and the signal can't get through. GPS is a line of sight system. And that means line of sight between you and the satellites. If the satellite can't see you or you can't see the satellite, then you're not going to get the signal. Okay, so it's more than just the receiver, it's the person running it.
Hey, Peter, we also have in PointMan a way for you to say, hey, this is the minimum accuracy you require, and PointMan would stop you from taking any points. If you fall below that, it'll send you an alert, right?
That's correct. We have alarms, and your project manager sets that up and says, okay, I'm not going to accept any measurements below. It has to be a RTK fixed solution, and it has to have this kind of horizontal or this kind of vertical accuracy. That's all set up by, based on your project. And what it will do is either warn you if you set that up, say, hey, you're not really within accuracy levels that you set, or it will outright refuse to accept that. All depends on how you want to set it up.
Yeah, this sort of prevents you from somebody taking the measurement and then coming back to the office and say, oh, it's not the right accuracy. And so you can set that up in PointMan and prevent those points from saving.
Yeah, absolutely. Okay, next question. You mean that your solution is compatible with all GPS antenna manufacturers like Trimble Topcon? Yes. I mean, again, as long as it is able to initiate a Bluetooth connection to our system, and most of them can, then yes, we can pull off the data. The data comes what's called an NMEA string. This is a standard and supported data stream that comes from almost any, commercial level GPS system. So if we can read that, and you have the ones you have there, Leica, Trimble, Topcon, Bad Elf, we also have the Gold system, EOS Golds, all those we are compatible with and can use. We are, we always, looking at Trimble as well, because we are a kind of a partner with them, and it does a lot more because we have access to the Trimble SDK, but that shouldn't concern you. Yes, we can use most GPS receivers. Can point man solutions handle moving platforms? Sure. It makes no difference to us. Limitation on a moving platform, though, is, and it's not a point man limitation, it's a limitation on GPS. Your accuracy is going to suffer a little bit. Depending how fast you're moving, the RTK solution is a little bit noisier. But, within reasonable speeds, sure, that's not a problem. Confident on the accuracy number? We're not doing anything with the accuracy number. That is directly from the receiver. So that, in this case here, that accuracy measure of 10 centimeters in this case here that you're seeing is what the GPS receiver is reporting. So we are just bringing that right along to you. The confidence level on that is 95%. And that is a standard accuracy and confidence level. You're not able to use an onboard GPS antenna with RD200G or RD8100 PDLG with point man. Point man indicates it cannot receive the GPS data from that. Okay. That's something I'll talk to support about. I don't know anything about why not. And let me write this down, Larry, and I will get support on that for you, because you should be able to receive the GPS data from them. Most likely, it's a Bluetooth connection problem, and we will figure that out for you. Can point man solutions handle receiver data latency issues? Is that what you're referring to as is the differential age between the base and rover? I'm again not really quite sure on that. Differential age is, and we have that here, is if you have this is when the base station has sent out its corrections to you, that's the age of those corrections. If you're looking at 2 seconds, that's perfectly fine. When you're getting up to about 30 or 40, then you're getting a lowering of your precision, not your accuracy, your precision. It's getting a noise issue. This is a function of the receiver itself. Okay, so again, we are not changing the data we're getting from the receiver in any way. We are taking it as is and showing you this is what it is. So that's what you're referring to. It is not handled by point man, it is handled by the receiver, and the receiver is the best place for that to be handled because it can model time latency internally itself. We're not doing it. Hang on.
Yeah, I also typed in our help URL so people can read more about what our system support, what point man supports, and so on.
Yeah. Okay. Have I answered all the questions here?
I think you have.
Okay. Again, well, everybody, thank you for being on this call with us. Again, if you have any further information that you would like to get or more details on GPS or the point man solution, feel free to contact us, and they'll either answer for you or they'll send along to me, and I will do my best to find your solution for you.
Hey, Peter, can you put up the last slide so that they can?
Sorry.
Yeah.
I'm sorry. There's the support address, and they'll find me. They're very good at that. Okay.
Well, everyone, thank you for your time. If you have any questions, then feel free to channel through Anamika or directly to our support, and we'll be happy to answer. We look forward to working with the radio detection.
All right. Thank you very much again. And again, happy to present anytime you need. Cheers.
Thank you, Peter.
Thank you.
All right. Bye.